to another video. I know it's been a while, it's like 3 weeks since I posted my last video, but I had a lot of exams which I finished now, and I'm back to my projects, or well, I try to be. For now the robotics project is really taking a lot of my time, and I'm going to show you what I've been doing for it. So here we can see the 3D model of the robot. It's really made to be simplistic, easy to make out of all the components, and that's basically the explanation of why it looks so simple. If you can take a look, that this is just a steel plate, 1 mm. It can be bent around these corners to increase rigidity because of the moment of inertia for bending. Same for the underplate. And these brackets over here, these are made to guide a pole that will be an optional thing where we can attach a pole to the holes and make the robot jump guided, but this is just a precaution for us if it doesn't work properly, so we can kind of ignore it. So if we take a closer look at all the individual components, we can see two legs, and basically the legs are made of aluminium. They will be milled out, and this is a spring. We have the spring dimensioned at about 30 centimeters, 400, about 500 newtons. So it's a very stiff spring, but the motor should be able to handle. This is the disc where the crank mechanism is attached to. As you can see, if this will move, it will create a jumping motion, because the spring will then put all the force on this piece. That you also can see is that there is a arm that goes like this, which will create a torque or a moment around this point with a concentrated load from the spring. So this piece here and this connection will have to be very rigid. And if you take a closer look at the rest, so this is connected to the motors, which we'll see later. So this is very simple. This is I'm not sure how to call it, but it's bearing, and it can move a little bit in here, so when it's not aligned, it won't set huge stresses on this joint or this joint. And well, that's basically it. That's a very simple method. And this leg is then guided by this servo, which can change the direction of the leg, and so it can come down, it can can store all the incoming energy when you land or when you start jumping. The angle can be very determined. Also, this is supposed to be fixed onto the point. We made this so that the servos are not properly dimensioned, because we have several servos and this is not fixed yet. So we made these guiding slides, and this, if you take a look at this PCB, this is PCB. It has two photo interrupters, which then have an encoder disk that is attached to this rotary plate, so it can determine the angular velocity. It can also determine the position of the rotary disc, and it can then also determine the position of the springs. So this is a very important part on the feedback control. And if we take a look inside, so if you can see inside, we have a lot of components right here. First of all, we have the motor, which is a DC motor, which is connected to a gearbox, which can output 20 Newton meters of torque, but it also drains about 40 amps of current. So we will have to design a circuit that's able to handle such currents, and we will take a look at that very soon. Then this motor is kept in place by these motor brackets, and the gearbox is also put in place by the motor brackets, and then we have a piece that is specially machined. Well, it has to be specially machined, and this is basically a part that, here's the bracket that will hold this piece. The torsion axis is going through here, and this is basically made so it doesn't slide or it doesn't move, but it can still rotate. And there's also this piece, which is the piece that is clamping everything together. And I think, yeah, this is the same piece again. This piece is basically the leg, and this one hole is misaligned, which is already fixed, but not in this model. And that's basically the drivetrain of this leg system that we made them. So it's just a motor to gearbox to this rotary disc, which is basically which has a square hole in the middle. My only concern about this is the stress concentrations in these corners. Usually you use a hexagon or something like that for a better stress concentration distribution, but it's harder to machine. This is basically just cutting these holes out and then finding a way to make these corners straight, or we can just minimize these corners by just filing away little bits of pieces where we have more corners, and therefore we also have less stress concentrations. But it's also harder to find an axis that's able to hold the high torque of these motors, and everything is being held together by bolts and such. and on the other side is basically everything the same. And this little green thing is the PCB that's going to fit in here. As you can see, it has already 4 MOSFETs attached to it. That was because I'm going to use this big steel plate as a heatsink, because why not? It's also going to be 40 amps each, therefore that's 80 amps per 4 MOSFETs. And now if it's easier to explain the mechanism, so I'll try to explain the mechanics. Okay, so we will start in a rest position. It's basically like this, or we'll see what's most stable. Maybe it's these legs a little bit spread. Oh, this component is fully defined, but a little bit like this, so that it stands stable. Maybe we'll have to find out. And then it slowly compresses the spring. It doesn't intersect with the part yet, but I think you can imagine the spring being compressed in this state, and then the leg is put in position. Basically now the center of mass is pointing down. If I can see, if I find the center of mass, I have to rebuild this. Center of mass. Oh. Right here. Oh well, I can see the center of mass. It's right there. That's actually the moment of inertia, but it's also the center of mass. So as you can see, if I can align this, it's a little bit slow because there's a lot of components in here. But you can see there's an alignment, not that great, but that's intended because the body will then fall down, and if you can align this to be something like that or something, but it will then rotate this disc with very high speeds, about the speed of the spring. It must be, because as you saw in my last video explaining this, there must be a relationship between the speed and the angular velocity of these motors. Therefore we have this rotary encoder to feed back to the computer what speeds it must rotate, and then this spring will have full force in the body because there's ground here. So all the force will be directed into the body, and the body will go upwards, and then the sensors then calculate what angle the leg must position so it can come down, direct all the upward force and momentum into the springs, which will then shift momentum upwards, and then the surface must be really quick and align with the momentum, which can then make sure that the robot doesn't tip over, but basically use the momentum in its advance, where it can then deliver this force again in the same direction, collinear with the momentum, making sure the robot jumps well and there aren't really bad interferences with momentum and gravity and such. So that was the basic mechanic principle. I hope it's going to work out, because it's going to be pretty hard to calculate all these angles, but it's going to be pretty fun, I hope. So let's take a look at the control circuitry, which is basically the whole thing that's going to make this operable. So first of all, we have the microcontroller. I have made this little block which just simply shows all the individual pins. It has to represent this microcontroller. It's much better than the Arduino, which I also have here. It's a little bit smaller and it has a lot more PWM pins. It has 10 on the upper side and it has about 4, I think, on the back side, where this has only 6 or 8. I think it was 6 PWM pins, which is not sufficient, and you will see why. This is then the buck converter. It just takes the battery voltage and steps it down to 7.8, which is the driving voltage, maximum driving voltage for the servos. And it has to, and they draw about 1 amp of current, which has to be pretty well regulated. And then we just feed that voltage into some linear regulators. And then for the main circuitry, this has to be linked up with a pair of headers. It's not yet wired up, but it simply just takes this input to here. These are the headers. What this says is we have VCC, we have 8 MOSFET controller pins, 2 servos and 2 for the rotary encoders, and then we have ground. So what happens first? MOSFETs 1 and 2, they get fed into these headers. We have headers for the Arduino Nano, and we have headers for the other microcontroller, which is basically using inverted output for only using, I think, 4 plus 2 servos, which is 6 PWM pins, which is exactly for the Arduino Nano. And then we can see the input being kind of filtered by resistors for transient. It's also the 5 volts coming in, it's being filtered again, bypass capacitors. Here we have shutdown, PNP transistor, which is going into the shutdown of this driver IC. We have the digital voltage input. We have the high in, which is 1 MOSFET, 2 MOSFET, low in. We have VSS, digital ground, which is, I simply just connected that to analog ground. And then we have the high out. We have voltage in bootstrap and voltage source, VCC, ground, and the low output. You can see VCC is here, it comes in VCC, it's being directed by this diode through a current limiting resistor into this bootstrap capacitor with bypass capacitor. Then it's basically double VCC, which is required. It's about 30 volts in VB, because this is a charge pump. Charge pump is boosting the voltage to 30 volts. 30 volts
that's relative to the voltage at the source of the first high-side MOSFET, which is, if it's conductive, it's VCC, let's say 15 volts, and it's 15 volts over here, 15 volts at the negative, therefore minus 15 relative to plus 15 volts is 30 volts. Therefore every time this one is on, we have 30 volts, or else we have 15 volts. Therefore we don't go above the 20 volt threshold, because that would fry the MOSFET, which is not good. So that's just basically being fed into this current limiting resistor and discharge diode, pull down resistor over here, and same over here, low side. This is much easier, there's no need for bootstrap, which is then being fed into this safety AND gate. This AND gate determines if this one is on, this one is on. That's basically direct short, and these signals are determined by the microcontroller, which is based on our human programming. Therefore there's a possibility that both of these gates will turn on accident, and this is just a security measure, which then the input then goes to the motor, and we have basically the same, exactly same driver over here, just different PWM signals. Therefore we can make the motor go one way or the other, and that's required because we want to also deliver a counter torque, because a counter torque makes sure that the spring isn't extended too fast, or that the spring has a load what it can push upwards. And if the motor delivers counter torque, it's basically a counter force for the spring, and therefore the spring will push against the motor, and the motor is attached to the body. Therefore the body will go up because the spring is pushing against the body. So here we have safeties, safety 1, 2, 3. Here we have the exact same 1, 2, 3, 4 safeties. This is basically a current hall sensor, which is detecting all the currents that's going in, because that was also required for the rotational speed settings. Then we have the I2C over here. That's able to measure the position of the body, and this is just a simple distance sensor. All this safety is going into this Darlington array, which will then be connected to this PNP transistor you saw earlier. So basically this is always on, therefore there's no way. So this digital input is being pulled to ground, therefore this thing won't shut off. But when there is a voltage at the gate, the voltage at the gate is being pulled down, this will start to conduct, which will give a digital 1 at the shutdown, which will shut everything down. Because it's, in addition to high side driving, as you saw over here, I'm not very sure if I'm going to do that, because there's a lot of circuitry involved, and it all has to be made by hand. As you can see, it's a lot of work. So, but there's also another reason which I've simulated. If you run the simulation, what this basically is high side MOSFET, low side MOSFET with inverted signal, and a bootstrap. It's properly dimensioned, but as you can see over here, this is the waveforms. As you can see, can barely see it, but here we are. That's not fully being pulled to ground. It's floating at about 0.3 volts, which also means heat dissipation of about 100 watts, which is only able to deliver 200 watts at the output, which is 100 loss in the MOSFET. That's really a lot. And if this was making use of P-channel, I'm sure it would be less, but it also would introduce more conduction losses, as you can see over here. And this is the current. Red is current, blue is gate voltage, green is VDS voltage. As you can see, the bootstrap is working very well. As you can see, the VCC over here is nothing more than 15 volts VCC. Therefore this is about 28 volts, if you can see for yourself. 28 volts. Bootstrap is working fine, so I don't have to worry about that. But you can see my problem over here. So I'll see what I do, and I'll make a test setup on this little board. I'm gonna make it only this circuit, so I can pull the motor over here and test all the voltage drops across everything, and probe it with my scope over there. And I've also started to build the power supply for my railgun, which is nothing much than a converter yet. This is just basically all the MOSFET drivers has to be on here, the control circuitry and the microcontroller. But this has a little bit more priority, and that's about it. So I'm sorry again for the not so frequent uploads anymore, but it's very busy. But I hope I'll make some more videos. So thanks for watching.